All right, our last part of chapter 2.3 talks about higher derivatives. So we usually start with f of t or f of x, and we often think of that in velocity or in physics problems as the position in meters at time t in seconds. So then what is f prime of t? Think about that. That's the velocity, and its units, if that's in meters and seconds, would be meters per second. Then what's f double prime? So that's the derivative of the derivative. Well, if the derivative is velocity, then the derivative of that would be acceleration. And its units, so if we graphed velocity, we would have velocity in meters per second on this axis and time in seconds on that axis. And so the units of the derivative would be units of the y divided by units of the x. So that would be meters per second, which we often write as meters per second squared. So that's the acceleration. And if we graphed the acceleration, we'd have time on the x-axis and acceleration on the y-axis in meters per second squared. Now, in physics, we often like to deal with constant acceleration problems, but not all the world is constant acceleration. Like if you're sitting at a stoplight, you're not accelerating at all, your acceleration is 0, and then the light turns green and you start pressing on the accelerator. You went from 0 acceleration to some acceleration, and so your acceleration changed, and the rate of change of acceleration would be important. If you floor it, everyone's going to look at you, and your passengers are going to be pressed back in their seats. So we need to sometimes think about the rate of change of acceleration. That would be the derivative of the acceleration. If the acceleration is f double prime, then the derivative of acceleration would be f triple prime. And the name for that is jerk. And here's why you can think of it as jerk. Imagine you jump out of a perfectly good airplane with a parachute on, and you're falling, you're accelerating toward the earth, and you pop the parachute out. What happens? The parachute pulls you out by the shoulder straps, and it feels like a big jerk. So acceleration, if you know it's happening, you can kind of brace yourself for it. But if the acceleration changes, that's harder to brace yourself for. So jerk is a pretty important thing in a lot of physics once you get beyond constant acceleration. What are the units? Well, it would be meters per second squared per second. So it's meters per second squared per second, or you could say meters per second cubed. Another important application of jerk, let's say you're standing up on a bus because there's no seats, and the bus is driving along, and all of a sudden the driver has to slam on the brakes. If you knew the deceleration was coming, you could stand and kind of brace yourself. You could hold on tight to one of the poles, or you could put a foot farther forward to get ready for it, for that change in acceleration. So there are actual documents that study what's an acceptable amount of jerk on public transit, both in the forward-backward direction, the side-to-side direction, maybe even up-down. So there are people thinking important thoughts about this kind of thing. How about the derivative of jerk? That would be f quadruple prime, and the name for that is snap, as in I hope my parachute lines don't snap, I guess. I've never done any real problems with snap, but I've heard it's important sometimes. The units would be, just following this pattern, meters per second to the fourth. I've heard when they were designing the Hubble Space Telescope, they had to consider all the derivatives of motion up to snap. And then after snap, well, if you got something named snap, the obvious names for the next two are crackle and pop, after the famous cereal. And people ask me, is that really true? And I say, well, I read it on the internet, so it must be true. So I think those are the official names because they're on the internet. Now you might have noticed that once you get past like f triple prime, it's hard to count how many primes there are. So there's a shortcut way of writing these. Let's see, that was quadruple prime 5, 6. You can write this as f with a 6 in the superscript in parentheses. So that's the sixth derivative of f. This would be the fifth derivative, And now I pronounce that like f super 5. It's not raising it to the 5th power. That would just be f to the 5 without the parentheses. So we'd have f super 4, f super 3, f super 2, f super 1, and you wouldn't usually write this. But it does bring up an interesting issue. What can we say about the original f? Well, following this pattern, that would be f super 0. F is the 0th derivative of itself. So that's kind of a fun thing to think. Or how many times have you taken the derivative here? 0 times. Here's the really fun part. You can say the nth derivative by saying f super n. So we'd write that as the nth of t, nth derivative of t, of f. And we can say, well, if I have 6, 5, 4, 3, 2, 1, 0, can I do f super negative 1? And it turns out you can. That's called the antiderivative. It's the function who, if you took the derivative of it, you would get f super 0. And we spend a lot of time on those in chapter 5, not to spoil the punchline of the whole class or anything. But the really fun part is that it also works if n is fractional. So you can take the half derivative, you can take the 1.39 derivative, and it even works if n is complex. You can take the 3 plus 7i derivative of something. I mean, I can't, I've never studied it, but there are books about it. You could go check out of the library or something. So these are called fractional calculus. Completely not required for Math 120, but a lot of fun to think about. Here's an interesting quote from President Nixon in fall 1972. Apparently inflation was getting bad and was increasing, and he said, the rate of increase of inflation is decreasing, which makes it sound like everything's getting better, right? And someone in a math article pointed out that this is actually an argument about the third derivative of something. Inflation is the rate of change of the cost of living. The rate of increase of it is the derivative of that, so that's the second derivative. And then saying that it's decreasing is saying how that thing is changing. So this thing is talking about the third derivative of the cost of living. So the article said that's the only known time in history when a US president has used the third derivative in an argument. Our next video will be just a quick practice with higher order derivatives.